Here we go. Day two of notes for us. Today we get to talk about Coulomb's law. Now, um, both of the pictures on the screen for us become somewhat important for us as far as Coulomb's law is concerned. The reason being that when we look at these two, they help to explain really what is happening between the force um, of attraction or repulsion between these kind of particles for us. Okay. All right. So here we go. All right, Charles Coulomb is the one who is credited with kind of creating Coulomb's law for us, so to speak. So, all right, so that's our equation down there in the bottom right. So make sure that you do have that thing written down, okay? So Fe, the force of or electric force basically, is equal to K times Q1, Q2 over R squared, all right? So again, our electric force, that's in Newton. Right? K is the Coulomb constant, which we'll show you in a second here. It's 8.99 times 10 to the ninth Newton meter squared per Coulomb squared. Now, please understand the reason why we give you the back end of this. Let's get this. The reason why we give you this here is because that tells you what units we have to have. Now, the only tricky bit for us is really that radius in the bottom, making sure that that thing is going to be, you will see right there. Okay. Q is the charge of the particle. That'll be given to you. It may be given as E's, like 1E, negative E, 2E, negative 2E, stuff like that. All right. Separation between the charge again is going to have to be done in meters. All right. So, a couple key factors for us. More charge equals a larger force, meaning that if we have objects that are higher in charge, right? What's going to happen is that either that attractive force is bigger or that repulsive force is going to be bigger for us. Okay? More separation equals a smaller force, meaning that if these are farther apart, force is going to be smaller, right? Again, either to attract it or to repel it, one of the two. And then K is a constant, meaning that that's not going to change. That number, anytime that we use Coulomb's law, is always going to be the same value for us. This is a field force like gravity. So basically what that means is that the closer you get, the larger the force is going to be. The farther away you get, less force is going to be felt by it. So an object that's, say, 1 meter, this is 1 meter, but is here, is going to have more force than here, which will have more force than here, so on and so forth. All right. As you get further apart, it will start to shrink. The force will there. Okay? All right. 2 electrons are separated by 1 times 10 to the negative 6 meters. All right, let's try it out. So the first thing we ask, well, actually, this will be a question that you're going to see either as a part or as a last part, whether that's a C or a D part. Is the force repulsive or attractive? So because we're dealing with 2 electrons here, right, then what that means for us is that with our 2 electrons here, this should be a repulsive force. Okay? We want to know, what is the electric force between the 2 of them? Okay? That's our charge for our electron. So it's going to be a negative 1e, which is negative 1.602 times 10 to the negative coulombs. There's our Coulomb's constant. There's our radius. So what we know is we know both of those two have a charge of negative 1.602 times 10 to the negative 19th coulombs for Q1 and also Q2. K is going to be 8.99 times 10 to the 9th, and then R is going to be 1.0 times 10 to the 6th. Now, a little bit of discussion before we get too deep into this thing. When you're using your calculator, I'm going to encourage you to use parentheses, right? And maybe even do this in parts. So here's our setup for us, just like I talked about, right? Our Fe equals K times Q1, Q2 over R squared. Now notice I'm using a ton of different parentheses here, right? You can put this all in as one, absolutely fine, right? But the thing that I will say is you're either going to use the caret button, the caret button is the button right above the divide sign. Okay. Or you're going to go and use the EE button. That's the one right above the 7. Okay. The EE button allows you not to have to type in the times 10. All right. It just simplifies that, and that's calculator speak for us. Right. So what I did was I just started to simplify everything. So I took the Q's times each other, and I also squared the radius. Here again, I'm letting my calculator do the heavy lifting for me. So I'll take the Q's that I just did divided by the radius squared. So the 2.6 divided by the 1.0. Okay. Oh, what did I do there? Oh, I multiplied the K into the top bit. I don't know that I like that step. But anyway, all right. So then we take the 2.307 times 10 to the negative 28th, and we divide it by the 1 times 10 to the negative 4th. Now, for this one, when you're dividing by the bottom bit, make sure, please, you're using parentheses. Otherwise, it's going to completely be a mess for you. Okay? So once we do that, we see that our force is 2.307 times 10 to the negative 16 newtons. Right? Now, in your calculator, it's going to say 2.307 E negative 10. Right? Just make sure we translate that for ourselves. Okay? Now, something to be aware of. An electron has a mass of 9.11 times 10 to the negative 31st. So even though a force is that small, the A is still relatively large. So if I take 2.307 times 10 to the negative 16, and I divide it by 9.11 negative 31st, I get an acceleration of 2.53 times 10 to the 14. This thing is still cranking. It's still moving, meaning that these two are going to get pushed with a huge amount of acceleration. Even though that number looks really small, is a large force for us. Okay? All right. So another Coulomb's law problem for us. I want you to pause the video. Try and run this one yourself if you can. Okay? So try this out. An alpha particle and a beta particle are separated by 1 millimeter. What is the force between the two charges? You'll notice here, there's my alpha particle. It's basically 2e. Beta particle is simply an electron. Okay? So there's our answer for us. Right? If it's separated by 1 millimeter, we have to fix that number. So what we need to do is we need to make sure that we change that. So that's going to be 3 to the left. So that means we put 2 zeros in front. So once again, there's my alpha, there's my beta, and there's my millimeter converted into a meter. Right? Multiply them all together. Take the top bit, divide it by the bottom bit, multiply it by the 8.99 Coulomb's constant, and you're going to find negative 4.614. Now, understand, if we don't know that alpha is positive and a beta is negative, we're going to see this force being negative. That means that these things want to be attracted to each other, or are going to be attracted to each other. Not necessarily want. I don't know that they have brains, but all right. So when we look at a Coulomb's law problem, this is really what we're going to see. Okay? Hopefully it makes sense. Let me know if you got questions.